So in this video we are going to learn about electromagnetic induction. What is electromagnetic induction? We'll go for that. First of all, so electromagnetic induction, basically it is the phenomenon in which EMF is induced on a conductor which is connected to a circuit when it cuts or intersects the magnetic lines of forces. Now what that means, it means that suppose this is a conductor, okay, a cylindrical conductor. Now this conductor is placed in a magnetic field, and when this conductor is connected to a circuit, external circuit, okay, it means it is carrying current, and her magnetic field is there. And when this conductor moves, okay, it cuts the magnetic lines of forces, isn't it? It intersects the magnetic lines of forces. When this intersects the magnetic lines of forces, when this magnetic lines of force are disturbed or intersected by this conductor which is connected to an external circuit, then an EMF is induced. Now that EMF or current is induced. Now that is called induced current, okay, and this phenomenon is called electromagnetic induction. So it is said that it is the phenomenon in which EMF is induced on a conductor. EMF is induced on this conductor when it intersects the magnetic lines of forces, okay. So if you remember, I said that Ørsted was a scientist. He said that whenever current flows through a circuit, magnetic field is produced, isn't it? Now this is exactly the reverse of it, which was discovered by Faraday, that whenever conductor cuts the magnetic lines of forces, then EMF is induced. Exactly the reverse of it. Ørsted said that magnetic field is produced from electric field. He is saying electric field is produced from magnetic field, okay. So first of all, we'll go for basic topics, units which we'll be discussing in this chapter. So first of all, let's go for magnetic flux. What is magnetic flux? I have told you this earlier. What is magnetic flux? Basically magnetic flux is denoted by phi, okay. Now as I said, magnetic flux, it is the total number of magnetic lines of forces passing normally through a given surface area. It means that if this is a surface area, okay, then normally through it means right angle through it. Now in this unit surface area, how many magnetic lines of forces are passing? That is the magnetic flux normally, okay. So when it is passing, making an angle theta with the, now suppose this is a surface, okay, surface of area A. Now suppose the magnetic lines of forces B is passing through this surface area, then its magnetic flux density will be phi equal to BA, okay. Magnetic flux will be B into A, okay. But this magnetic flux, if it is making, this is normal, okay, normal. So if it is magnetic field is making an angle theta with the surface area, then the flux will be BA cos theta, okay. This is the basic concept. Now we'll go for the starting of this chapter from Faraday's law of electromagnetic induction. This whole chapter is based on this law, and we have read this in our junior classes as well. So I'll revise it. What is Faraday's law of electromagnetic induction state? It states that an induced EMF or current is produced in a conductor whenever there is a change in magnetic flux linked with that coil. It means the same thing as I said. An induced EMF is produced whenever it cuts the magnetic lines of forces, or it disturbs and intersects the magnetic lines of forces. Now the rest two laws of this Faraday's law of electromagnetic induction are that this EMF lasts only as long as this conductor is intersecting or cutting the magnetic lines of forces. It means as long as the conductor cuts or intersects the magnetic lines of forces, only till that time that EMF remains induced, okay. And the third one is that the induced EMF, it is directly proportional to the rate of change of magnetic flux. Magnetic flux means this magnetic lines of forces. So see, it is directly proportional. The induced EMF, it is directly proportional to the rate of change of magnetic lines of forces or magnetic flux. It means that जितना तेज ये इसको intersect और cut करेगा, उतना ही ज़्यादा induced EMF, okay. So see, we can basically write in symbolic form as induced EMF E. It is directly proportional to rate of change of magnetic flux, okay. Flux. Now rate of change of magnetic flux means magnetic flux is d phi by dt, rate, okay. Rate is denoted like this. So E is directly proportional to d phi by dt. So E equal to k d phi by dt, and numerically k is equal to 1, so it will be E equal to d phi by dt. This is our expression. Now this expression will be used throughout the topic, okay. So this is a very important expression. E is equal to d phi by dt, where d phi by dt is the rate of change of magnetic flux. Now the last thing we need to know about this chapter is Fleming's right hand rule. Okay, we discussed Fleming's left hand rule earlier. Now there is one Fleming's right hand rule which will come in use, not very often, but still it will come in use in this derivations. Now this is the last thing we need to discuss about, and then we'll go for the derivations. Now see, Fleming's right hand rule, it is basically the similar thing as Fleming's left hand rule. The formation is same, just denotions are different. Like this thumb, okay, this is denoting the direction of motion of conductor. Okay, it means the conductor, I said that this conductor is moving and then magnetic flux is changing. So similarly this thumb, it will show the direction in which this conductor is moving. Okay, this index finger, it is showing the direction of magnetic field, and this will give the direction of induced emf. So see, this is the direction of motion of the conductor, this is the direction of the magnetic field, and this is the direction of induced emf. Okay, suppose the conductor is moving upwards and the magnetic field is in this direction, left direction. Okay, then the induced emf will be outside the paper in this direction, outside the paper. Okay, so there is one more thing left, Lenz's law, but that Lenz's law will come into use when we'll be discussing about self-induction and mutual induction. So I'll not discuss Lenz's law right now. I'll just go for the derivations of the induced EMF in a straight conductor and the rotating coil. Okay, so the very first derivation of this chapter is, it is the induced EMF in a straight conductor which is moving in a uniform magnetic field. Okay, and remember, this is one of the most important topics in this chapter, and this question was even asked in the Hisan examination, and it is very easy, believe me, it's very easy, but one of the most important chapters, and probably the fixed question as well. So see, for this we'll just make a straight conductor. Let's make a straight conductor, somewhat cylindrical, you can make it. Now this is a straight conductor which is moving in this direction. Okay, in a uniform magnetic field. Now there is one thing, that this uniform magnetic field, okay, it is moving at right angle to this uniform magnetic field. This conductor, which is PQ, it is of length L. Okay, it is moving with velocity V in this direction, but it is moving at right angle to this uniform magnetic field. Now right angle, it is moving in this direction, so uniform magnetic field should be in this direction, right angle, isn't it? So we cannot show the arrow in this direction, we'll draw some crosses. Okay, so we will draw some crosses in this direction. It represents that the magnetic field is inside this paper, going inside this paper. Okay, it is moving in this direction and magnetic field is going inside this paper, right angle to that. So this is the magnetic field B, uniform magnetic field B. Okay, and it is moving in direction this. Now let us consider that in small time interval dt, this conductor moves through small distance x. Okay, it is moving in this direction, isn't it? So in small time dt, it will move through small distance x. When it moves in this uniform magnetic field, the magnetic flux changes and EMF is induced. Now we have to calculate the value of that induced EMF. So see, in small time dt, it moved through distance x. So area will be L into x, isn't it? L into x, the area swept by this conductor. This conductor, it moved through this much area, its length is L and breadth will be x because it moved through a x distance. So this area swept by it will be L into x. So we know magnetic flux linked with it, it is BA. We saw very first, phi equal to BA. So BA, it will be BLX. Okay, now we just need to do one thing, that we'll use the Faraday's law of electromagnetic induction, nothing else. So according to Faraday's law of electromagnetic induction, we have E equal to d phi by dt. Just put the values d BLX by dt. So B and L is constant, B is uniform magnetic field, L is the length, it will always remain constant. X can not be remain constant, because it means it can remain constant, or it may or may not remain constant, because see, it can move through this much x and itna bhi distance x ho sakta hai, x itna bhi ho sakta, itna bhi ho sakta. Simply B and L is constant, x is not constant, so B and L will come outside, dx by dt. Now see, x means distance, t means time, and distance by time is velocity, and velocity v. So BLV, this is the final expression, E equal to BLV. Easy enough, very simple. E equal to d phi by dt. Okay, phi is B into A is L into X, so BLX, and then just dx by dt is V. So this is the final expression. Now just one special case, that I said that it is moving at right angle to this uniform magnetic field. Had it been moving with making angle theta, then the expression will be dlv sine theta, nothing else. This is just one special case. dlv, just if it would have been making angle theta with the magnetic field, then the expression would be E equal to BLV sine theta. So this is one of the most important and one of the most easy questions of this chapter. Okay, now we'll move on for the induced EMF in a coil rotating in a magnetic field. So we are going to know about induced EMF in a rectangular coil which is moving in the presence of magnetic field. It is also one of the fixed questions. These both questions are very easy. Now we'll just consider a rectangular coil. Okay, this is a rectangular coil. It is moving in the presence of external magnetic field. Now let's consider two magnets, north, south. Okay, now magnetic field is in this direction. Obviously this is the magnetic field B. Now see, let us consider this non-magnetic rectangular frame over which wire is wound to form n number of rectangular coils, each of area A. Magnetic field is B. Okay, now this coil, it is rotating here. Okay, this is the coil. Suppose this is the rectangular coil. Now it is rotating here like this. Okay, it is rotating, and the axis of rotation is this. It is x dash, and it is rotating with constant angular velocity omega. It means it is rotating with constant angular velocity omega. Okay, now let's name it PQRS. Okay, now obviously in every half rotation, this is the half rotation, isn't it? This PQ will occupy the place of RS. In such a way it is rotating. Okay, now see, now just only one thing remaining, that is angle theta. Now what is angle theta? That is one of the matter of concern, so I'm gonna discuss it right now. See, so we know that angle theta is the angle made with normal, the angle made with the magnetic field and the normal of the rectangular coil. See, if this is the coil, the normal of the rectangular coil is normal always 90 degree to the plane. Okay, this is the rectangular coil, so normal will be in this direction, in outwards. Suppose this pen is the normal. Okay, this is the rectangular coil and this is the normal outside. So see, when it is normal, and this is the magnetic field in this direction. Okay, so this normal and this magnetic field, in दोनों के बीच का जो वो है ना angle, that is called theta. Now see, in this way, when it is in this condition, obviously it is 90 degree, field is in that direction, it is in this direction 90 degree. But when the coil starts to rotate, now see, the coil starts to rotate, the normal will also rotate with it. अब तो ये normal जो है इस field के साथ थोड़ा सा angle बना रहा है ना. So see, this is the field. Okay, suppose this is the magnetic field. Okay, and see, this is the coil and this is the normal. This black pen is the normal. So see, when the coil is rotating, when the coil starts to rotate, now this normal is also rotating with the coil, so it is making an angle theta. Now this angle between these two things, it is theta, that is the angle theta. Okay, and this theta, it is actually called the angular displacement, and angular displacement theta is omega t. Okay, these are the basic things we need to consider about this figure. This is calculation of this thing is also very easy. Only the one thing to remember is this theta, nothing else. That, and this theta was not there. Okay, theta का बात ही नहीं आया था, but here the angular displacement theta is equal to omega t. That's the only thing that we have to remember. Okay, so when it is making angle theta, then the magnetic field, now यहाँ भी वही चीज़ करना जो we did in the last thing, E equal to d phi by dt. So d phi means phi means B into A, so B का value we have to put. Okay, here we put the value of A, here we have to put the value of B. So see, we know E equal to d phi by dt, same electromagnetic induction का law, E equal to d phi by dt. Now here basically phi is B into A, but here it is making angle theta, so phi will be BA cos theta. I said you very early, if it is making angle theta, then BA cos theta. If it is not making angle, then BA. So it is making angle BA cos theta. So it will be d phi will be BA cos theta by dt. Okay, this is theta, not phi. Okay, theta, BA cos theta, and we know theta equal to omega t. First of all, we'll put the constant outside. B and A are constant, it will come outside, so it will be d cos theta by dt. So it was B A d cos theta by dt. Now for clearance I did it here. Okay, see, E equal to d phi by dt. D phi means BA cos theta by dt. So BA d cos theta by dt. Now we know theta equal to omega t. Okay, theta equal to omega t. So it will be d cos omega t by dt. So the angle should be same for this. Okay, for derivation, so it will become d cos omega t by d omega t. The angle should be same. Now we put d omega t here, so we'll for balancing d omega t, and the remaining one dt. Derivative, simple derivative. Okay, now see, derivative of cos is minus sine, so it will become minus sine omega t, derivative of cos. Now see, in this one, omega is constant, omega comes outside, dt by dt is 1. So the final expression will be minus BA omega sine omega t. Okay, omega t is theta. Again we'll keep here theta. Omega t means theta, isn't it? So sine omega t means sine theta. So this is the basic expression. Okay, this is the basic expression. Now see, there are n number of circular coils, so total value will be E equal to minus nBA omega sine theta. But one thing, this minus is not used in this. Minus is just showing that the direction of the induced EMF, it is opposite to the direction of the conductor. So minus is not used in that calculation. So just the expression we can write nBA nBA omega sine theta. Okay, this is the basic expression. Okay, now see, two special cases, very easy. Two special cases, that if it is perpendicular. Now one thing to consider, this is the only case when perpendicular mein angle 0 degree hota hai, or parallel mein angle 90 degree. I'll show you how. See, basically when we write that when the plane of the coil is perpendicular to the direction of the magnetic field, when it is perpendicular to the direction of the magnetic field, we assume that theta will be 90 degree because perpendicular terms comes there. Okay, but here consider one thing, that the angle theta, it is the angle between normal of the plane and the magnetic field, not the plane and magnetic field, the normal of the plane and magnetic field, uska angle hai theta. So see, when the plane of the coil is perpendicular, it means this condition, perpendicular, okay, to the magnetic field, then the normal will have direction. When it is perpendicular, it means it will be in this direction. Okay, magnetic field is in this direction. Perpendicular means like this. Okay, 90 degree coil. But see, the normal of the coil is in this direction. Normal of the coil. Okay, one thing. So I did this to make you understand. See, when it is like this, normal, and then it rotated and became perpendicular to the magnetic field. This blue pen is the magnetic field. Okay, now this coil, my hand is the coil, so it is perpendicular, and see, this black pen is the normal of the coil. Now normal of the coil and the magnetic field, they are parallel, because since this it is perpendicular, but this normal is parallel, isn't it? So parallel mein angle to 0 hota hai, so theta will be 0 degree in first case. Okay, theta will be 0 degree in first case, so E will be 0. And similarly in parallel one case, see, it is parallel. Okay, this case parallel, so parallel mein to angle, this normal will be in this direction, so normal and iske beech ka angle 90 degree. Okay, so it will be E equal to nBA omega sine theta, sine 90 degree is 1. Now remember one thing, this nBA omega, it is the maximum value of EMF. Okay, E maximum, which is E naught. Okay, so E naught is nBA omega, maximum value. Obviously maximum value sine 90 degree hone pe to maximum value sine 90 is 1, which is the maximum value of sine, so it is maximum value E naught equal to nBA. So from here we got that equation. Yeah, we used to write E equal to E naught sine omega t. We got from here, because see, maximum value E naught is nBA omega, isn't it? nBA omega. So normally we write nBA omega sine theta. So nBA omega means E naught, so E equal to E naught sine theta means omega t, sine omega t. From here we got, see, in this derivation we do not need to show this, I am just showing you for your information. From here we got that A equal to E naught sine omega t. Okay, so basically for derivation we just need to draw this figure, and what I explained you about theta normal and all, we don't have to explain it. Just draw the figure, give the explanation that it is rotating with an angle omega. Okay, constant angular velocity omega. So the angular displacement is theta, such that theta equal to omega t. Okay, and then just go for the derivation. This is all about the induced emf in rectangular coil moving in presence of magnetic field. Okay, and this one also, if you didn't understand, you can rewind the video and see it. So this is all about the electromagnetic inductions basic topics. Now further we'll see about self induction and mutual induction. That will be the last topic of this chapter. Well, thank you for now.